Okay, thank you very much for the nice introduction, and also thank you very much for this opportunity to come and visit IAC. In fact, this is my first time in IAC, so I'm very happy to be here and meet you all guys and also present my research in front of you. So today I will be talking about precision physics at particle colliders. Basically, what is the relevance of doing a precision studies in specifically for the collider phenomenology, and from the theory side, how can we do precision calculations, what are the methods that will be useful to do such kind of calculations. So these are the things I would like to discuss. So today I will be giving a very brief overview about that, and tomorrow I'll detail about it. Is that okay? Okay, sorry. So before I discuss what I meant by the precision and the relevance, let me start with a very brief overview or a kind of brief history. So let us start with the very broad question, that is one of the fundamental question, that is, what are the fundamental building blocks of nature? Like everything that we see in nature, what it is all made up of? And is there a physical principle that determine the dynamics that we see from very small scale to the larger scale? Of course, this question is not a new question. This is a fundamental question that driven physics where we are right now. And our understanding about the fundamental constituents has changed over different time. So we don't need to go back very early in time to understand that. Even when we look at the past century, like in the beginning of the 20th century, the idea we had about the fundamental constituent was, like the picture we had was, everything is made up of atoms, and then atoms can be comprised of nucleons, like the protons and neutrons and the electron. This was our picture. But later on, in the middle of the 20th century, there has been the situations, specifically from the experimental particle physics, that we have come up with many new particles, which the properties of which we cannot explain much from the theory that we have at that point. And this has led to the the breakthrough idea that all these protons and neutrons and whatever is all the new particle that we have come across, all these are basically made up of more fundamental particle, which is having a fractional charge, and we call them right now as quarks, and there are gluons as well. So this is the picture we got in the 1960s, and later on this theoretical idea has been proved to be true from the experiments as well. And later on this has basically made to much more theoretical principles and combined them together to get to the current picture that we have about the physics of elementary particles, and which we call as the standard model of elementary particles, which basically contain all the fundamental interactions, the 3 out of 4 fundamental interaction, that is the strong, electromagnetic and the weak interactions. And like if we just simply write the particle content of the standard model, this is the most simplified form of that, where all the matter particle has been organized in a quarks and leptons according to the properties. And then we have the mediators of these fundamental interactions, which are called the gauge vector boson. And then we have the Higgs boson, which was introduced in order to explain the mass of all these elementary particles. So this is the simplified picture, and which is very well established for explaining the principles of elementary particles. Okay. Of course, as I mentioned, not just the theory, we need the theoretical intuition with experimental support in order to get the picture that we have right now. So it was always, the role of collider physics was always there in order to understand the structure of this subatomic world. So at the moment what we have is the Large Hadron Collider, which is the most powerful collider where we can collide the proton with very high energy, such that through this collision we can produce some new particles which we cannot otherwise really detect or measure. So through this controlled environment with very high energy and very high luminosity, we can produce we can collide the proton to give rise to a situation which is very close to whatever was the early universe condition. So from there we can measure such kind of scattering events, how much will be the probability of such kind of scattering events, and that can be verified from whatever the theory predictions. Okay, so we have both the theory predictions from the standard model, and we have also collision measurements from the experiments. Now, in the last 50 years, there has been numerous test and verification between these theory predictions as well as the collider experiments, And it could be seen that this is like some plot showing the n number of such scattering productions, which basically is the measure of how much we can, whatever is the scattering probability of such kind of production to happen at the colliders. So we can see that these are the different experimental measurements, and then there are theory corrections coming from the standard model. We could see that all of them are like pretty much matching within the uncertainty from the theory as well as the experiments. So it seems like everything is pretty much consistent, whatever is the theory prediction. So does that mean that we have? Yeah, for example. Yeah, what I meant, for example, if we take a Z production at the LHC, okay? So what it means is that Z production along with 6 jet or Z production along with a single jet. So this you can produce from the experiments and get what is the value corresponding to that, okay? Similarly, starting from the first principle of the standard model having the Lagrangian, and from there we can get the theory predictions from the standard model, okay? And that is what it is given from this gray band has given from the theory. Oh, the production cross section, the production cross section here, yes. So when we look at that, you can see that whatever is the standard model value gives us and whatever is the measurement is giving, what is the value. Of course, there are uncertainty, but that is still within that, whatever the value is within that range of this uncertainty. It's not very, yeah. So uncertain is the size of that. It can, yeah, for some of them it is very big, and some of them you can see it is from the standard model. Some actually from the standard model we cannot really get the mass. What could be the mass for that? Yeah. Yes. This we have to fit from the experiments. Through many experiments we can fit what could be the things. Yes. There could be probably some exceptions which I don't really see. But yeah, otherwise it is really a standard model. Yeah, everything is there from the theory. At the moment, LHC collision energy is 13.6. This is basically what could be the production cross section, the amount of cross section basically. And for when we go lower means it become much rare process. That is what actually it means. Like for example, this production is much higher, that you can see more in the experiments. But when you go more in the lower, that means it is much rare process, because it's their probability to do such kind of scattering event is much less. So that is what I mean by the rare process. Yes. So I will be coming to that point, how we do that thing. Okay. So we see that whatever we see the experimental measurements from the collider, they are pretty much matching with the standard model. So do that mean that we have already got the complete picture from the standard model itself about these elementary particles? That is not definitely the case. There are more into whatever we have. For example, this is the standard model that I mentioned, but we also have other observation, astronomical observation, that of course what we see from the visible universe is only 5%. There are more into it. There are dark matter, evidences for the dark matter and dark energy. Those things we don't have any explanation from the standard model. We have other things like we have matter over antimatter, dominance of matter over antimatter, which we don't have any explanation from the standard model. Yeah. Right now it is around 3-4%. It is not all of them. It depends on the process. For some of the process from the theory, this uncertainty basically comes from different sources. Okay, it could be coming from because we don't have higher order corrections, which could be coming from that. We don't have from the coupling constant, it could be coming, or mass, it could be coming. So there are different sources, and PDF also one of the source. So running coupling, yes. And in some of the things which we already have enough higher order corrections, but PDF we don't have much. So that cases PDF dominates. So there are some cases like that, but it is not a general. So yeah, for example, some of the thing here, we can see it's a lot of corrections, and that is not really not from just from the PDF. It's the total theory corrections are large, and depends on the process. Okay, so there are we have evidences that there are other things. This one. This one, oh no, it's actually from the, let's see, from the collider. I did not make it is from the Atlas experiment, yes. Yes. Yeah, in one single plot. Actually, yeah, I could show some other things specifically for him, like how coupling constant has been measured and how it is really matching with whatever is the theory predictions. But I thought this has a lot of things, so I just took this as an example. But there are many such examples that we can show. Okay, so there are many things that is beyond the standard model. We have the evidences for that, which standard model do not have explanation. And within the standard model itself, we are yet to understand many things. What I meant is that, for example, neutrino, we have neutrinos from the standard model which do not have mass according to the standard model prediction. But there are observations that it has, even though it is very slight, there are masses. We don't know from the standard model what is the explanation for that. And even the Higgs boson, we found this particle, like all this particle content of the standard model has been already observed in the experiments. And the last one was the Higgs boson in the last decade. We found out that. But we still are studying whether it is really the Higgs boson predicted by the standard model. It has the properties predicted by the standard model. So those are still exploring, or it is something like some composite particle, or whether it has, like standard model predict it itself, it interact itself. Those kind of things we are yet to see from the experiments. So we are still exploring the standard model itself from the experiments. So we know that there is something beyond the standard model. Okay, for example, here I wanted to show that even after the Higgs discovery, there is still fundamental discoveries from the experiments. For example, one of them is in 2016 and 18, we found out a observation that Higgs is really coupling with the fermion. So from standard model, that has been predicted that the Higgs couple with the fermions, and that gives the mass to the fermion. Similarly, Higgs coupled to the gauge boson, and that gives the mass to the gauge boson. And it has seen that it is experimentally observed that that is actually, as per the standard model prediction, that is according to the coupling of this Higgs boson with the particle, that decide how much will be the mass of the particle, or coupling would be proportional to the mass of the particle. And we could see that that is really matching with the experiments, whatever we see. But it's still, because we see that it is matching with the experiment, that's why we don't really celebrate that. But this is also fundamental discovery that even though its standard model predicts, but those kind of things we are still exploring at the LHC. Now recently there has been also first evidence that Higgs really coupled with the second generation fermions, second generation leptons. For the second generation fermion, there are like first hint is there that we are still exploring. And there are more things to it, like for example, Higgs interaction with itself. We are not yet in a position to tell about that, what could be the, like from standard model it is there, but whether it is really we can see from the experiments, those are still exploring. So probably in the next upcoming colliders will give us something about that, and if it is really do not match with the standard model, probably that will give us to something, some theoretical idea beyond the standard model. So it is really important that we go beyond and find out what could be the, but where we can see the breaking point of the standard model. Now, from the experimental side, there has been numerous efforts to find out something beyond the standard model, whether we can see some new particle, some heavy particle searches that has been not predicted by the standard model, and there has been many such kind of efforts. It has been even gone to few TeV scale. But unfortunately, the thing is that we are yet to find out something, anything beyond that until now. So there is not yet any direct evidences from the current experimental reach for something beyond the standard model. So that is when the relevance of precision physics comes up. Like what we can do is that an indirect way to do this is that we can go beyond whatever we have already, we can go to the precision measurements, and then we can also get the precise theoretical predictions, and getting the tiny deviations between them, and from there we can probably find out there could be some rare process that we can really find out. So that is where the relevance of precision program comes up, and what we can do is that we look into the more details, and the more we have, the farther we can go and try to see for the, like, say, try to probe the like rare processes. So that needs both the precise measurements as well as precise theoretical predictions. So here, just to show, I have put a cartoon here. It's really just a cartoon. So we have some observation, for example, a differential distribution. From the current experimental reach, this is the area if we see, and this is the standard model prediction. For example, if we don't see any kind of direct evidences, the reason could be such that either such kind of new physics effects are something beyond the whatever is our experimental reach, which we cannot really detect right now. Yeah. Yeah. I don't think it is settled yet, but probably I am not the right person to tell this. I can look about it. It's, yeah. Yeah. But that may probably give us something new, right? Okay, so here what I wanted to show is that if there was a direct resonances of new physics that we would have been already seeing from the experimental reach, but we could not see that. So the reason could be either that such kind of things, effects are beyond whatever is the experimental reach, or it could be something that is hidden within the, like, because it is so rare, it is hidden there. And if we get much more precise predictions from the standard model, such kind of rare process will be, like, we can probe such kind of rare process. So that is why it is like there is an indirect way that precision physics opens up to find out such kind of probe where we can probe the rare kind of process. Okay, so this is why precise where the relevance of precise measurements and precise theoretical predictions comes up. Now from the experimental side, there is already a well-defined plan, at least for the next like until 2040. So our current analysis from the experiments is it's at the luminosity of 190 femtobarn inverse, and by the end of high luminosity LHC, where we will have more data, like 20 times more than whatever with the current analysis. So that from there we expect that whatever is the experimental uncertainty from the statistical uncertainty, that will be reduced to the factor of 4. And even beyond high luminosity LHC, there are also proposals for other upcoming colliders like electron-positron collider or like very high energetic colliders. So there are proposals from the experiment itself where the aim is to get the precision of like percent level precision or even like less than 1% uncertainty. So in order to explore such kind of potential from the experiments, it's crucial that we also have the theoretical predictions to that level of precision. So that is exactly where the precise theory predictions, relevance of the precise theory predictions comes up. So I hope that I have convinced you that why we need percent level precisions from the theoretical calculation. Now let us see how we compute really from starting from the Lagrangian of standard model, how we can get something that is really useful at the experiments. So let's see little details about that. So when we look at the colliders, as I mentioned, what we collide is the proton beams. It is not really what we collide is the fundamental parton like quark or gluon. What we really collide is the proton beam. So it's really a kind of huge number of events happens in the experiments, but this picture is really a simplified picture of that because that is what I will be focusing on. So let us take this simple picture where a single parton from proton beams comes up and that collide, like there is a parton, for example a gluon from a proton, another gluon from a proton, that collide together to give rise to something interesting, for example a Higgs boson, and then it decays to a quark-antiquark pair. So what we are interested in is this, it's called hard scattering, that is the partonic level cross section where we can measure the probability of such kind of events, and from the theory we can really compute this kind of partonic cross section using perturbative methods. So what we are interested in is computing this partonic cross section from this from the theory methods, and then we can also incorporate with PDF, that is parton distribution function, which is basically the probability of such parton to get from the proton. Together with that, we can get what could be the hadronic level cross section that we can really experimentally match. Yeah. In the external state, what you meant? Yeah, these are the gluon will be the incoming particle. Okay, from the experiments, yes, these protons are colliding. So when we collide the proton from very, very high energy, we can really probe the internal structure, and that is what we assume that this parton, that is the quark or gluon inside the proton, will be colliding in that high energy. We don't really see that in the real picture, but that is happening, and then with detectors we will get whatever is the final state. So in this picture, incoming is the gluon and gluon. Two gluons, and that give rise to the Higgs boson, and then decaying to quark and antiquark pair. So yeah, so from the theory, when we calculate partonic cross section, incoming state will be gluon and two gluons. Yes. Okay, so why we can use perturbative methods in this kind of computations? The reason is that the amount of the energy at which we do these partonic level interactions, at that energy, the strength of the interaction, that is the coupling constant, is very small. So we can use the perturbative methods by organizing the cross sections in terms of the power series and the coupling constant. So basically, partonic cross section, where the building block is basically scattering amplitude. So we can express this scattering amplitude in terms of a perturbative series. Here I have taken the QCT coupling constant. It could be electroweak coupling constant as well. Now there will be leading order, next leading order, and next leading order, and so on and so forth. And we compute the coefficients of this amplitude by using Feynman diagrammatic technique. So what I meant here is that the leading order will be the tree level Feynman diagrams, where basically this electron positron collide to give rise to the QQ bar pair. We can write in terms of a tree level diagram, which is really a rough estimate. When we include quantum corrections to that, we have to also take care of, there is a gluon in the loop, like we have to also take care of, it could be create and annihilate a gluon could be there, or there could be a gluon that is in the final state, real radiations. So this both will come to the same power in the coupling constant. So we have to take care of this virtual or loop corrections, or we have to also take care of these real corrections. And when we go beyond the next leading order, that become more interesting with like double virtual corrections, real virtual corrections, double real corrections, and so on and so forth. So this adding this next leading order generally increase the precision by 30 to 10%, the uncertainty reduced by that. And when we include the next leading order, it's like almost 5% precision. Yeah. It's just an example I have given. Just to see the how much we really need to go in the perturbative prediction, I have taken an example. We can really take Higgs boson production as the example. For example, if we take Higgs boson production from the gluon fusion channel, if we only consider the leading order, whatever is the theory predictions, that is very much different from whatever is the experimental measurements. If we only take care of the leading order, there is a large differences. But then this, when we get to the next leading order correction set, we can see that it enhances the theory predictions. It is better, still not really comparable with the experiments. There are still differences. And if we, from the theory, for example, if we only had until NLO, we could be thinking that it is something coming because of some new physics effects. So that is why we have to go beyond and see that the next leading order gives at least accurate result. There are still uncertainty coming from the theory, but still it is a bit, it is within the range of whatever we get from the experiments. So in the current, like for the many process, it has been seen that next leading order usually gives the accurate theoretical result. But we have to go beyond that to see, to get better, like precise things where we can say that if we have beyond that, it's a better, like uncertainty has been reduced from the theory. And it is now around 5% is the uncertainty. In order to get to the 1% precision from the theory, we have to even go beyond, and probably that will give us something about more rare process if that exists. So actually, this is actually I have taken a plot from this person Grazzini, so that is why it is MG. So from here also you can see another thing, that is how long it has been taken in order to go from leading order to next leading order. It took almost 20 years to calculate that at that time. Right now that is not the case, but at that time it took around that much time. And then from next leading order to next leading order, it took around another 10 years, and then so on and so forth. So this basically tells that the yes. Yeah, central value that actually say yeah. So basically it also shows the convergence of the series. Like we don't need to go really up. It after some point it get converged. I mean, yeah, up to some point. Not really. It is a asymptotic series. At some point it. Yes, exactly. Yeah, that is true. Yeah. Yes. So right now, so there has been corrections from the logarithmic accuracy as well. So what you can see is that at some point we have logarithmic terms in the calculations, which in some phase space region there is a huge difference in the scales in the logarithm, and that give large corrections. So it is so large that it will actually overcome the suppression from the coupling constant. So you cannot really use the perturbative methods. Does that make sense? Like whatever is the alpha s power, there is a coefficient. If that coefficient contains large logarithms, and together it will be like order 1 terms. So that means you cannot really truncate the series and you cannot use the perturbative methods. And such cases, you have to modify the series in such a way that these logarithms are also taken care in the coupling constant. So it is like a modified coupling in the series. So basically by doing this, you make better precise for this logarithmic correction. And those are called, and there is a series like that, LL, NLL, where you take care of these logarithmic corrections to all order in the perturbative theory. Does that make sense? Yeah. Why they did not include the NNLL? That is, oh, okay. So, I mean, I mean, they can include, but they did not include. So here we have that calculation. Probably at N3LO there is no calculation at N3LL. So that could be the reason they did not really include. But sometimes what happens is that when we have the resummed corrections at NLLL, N3LL, it is already very small. Probably it does not, like even though it reduces the uncertainty, but not much enhancement. So that could be the reason. Or it could be just no reason. They did not take it up here. Yes. So exactly. Yeah, exactly. So there are different phase space region, like when it is very, for example, for Higgs production, in the energy scale when the energy scale is very close to Higgs mass, there you have to take care of these kind of logarithms. Or yeah, so there are different region where you have to take care of this. Yes, not the entire region where it will be. Yeah, so what I wanted to say is that, so this also shows that there is a kind of theoretical challenges to go and to get these higher order corrections, and that is exactly what I want to say next. Like how do really we get the amplitude? Like how are we get this from the standard model Lagrangian to how we can get this amplitude? Okay, so as I mentioned, most of the time what we do is Feynman diagrammatic techniques. So whatever is the coupling constant, power of the coupling constant, whatever is the corresponding Feynman diagrams contributing to that coupling, we calculate the contributions coming from there. So it's really the sum of the Feynman diagram. For example, if we take a process where there is a production of Z boson and 2 photons coming from the QQ bar annihilation channel, when we look at the diagrams that contribute from leading order to next leading order to next leading order, we can see that there is a kind of rapid increment when we include the higher order terms, higher order corrections. For example, this is one example with there are 100 more pages. But is that really is the problem when we to get this kind of corrections? The thing is that it is not really the case. Like right now we have computers to handle such kind of large number of diagrams. So yes, it is actually 2 loop is there in the picture. Yes, it is next leading order, the next leading order. So 5,000 diagrams are not really a problem. Like even at the one loop case, we can have things like 50,000 diagrams or 100,000 diagrams. That does not really make a problem because we can handle them already. But what really is the problem is that when we try to, like, when we go up with that and we try to decompose them in terms of different building block, somewhere we lose the information, like we lose the simplicity of the amplitude and we lose the symmetries, like it is hidden, the symmetries are hidden there. So we don't really get the simplicity and the symmetries like manifested in the structure. It loses at some point in the intermediate steps. We can see that at least for the simple process, when we get to the final step, it becomes much more compact and simple. But in the intermediate step, that is not the case. So when we go to very complicated calculation, we cannot really go ahead with the things. So really how we can decompose them into a good building block is the problem. For example, at the next leading order case, if we consider, we take any one loop calculation. It could be any arbitrary number of legs, like 2 to 2 or 2 to 3 or 2 to 4, any arbitrary legs. We know that these kind of things, this amplitude, we can decompose them into basic building blocks called box diagrams or triangle diagrams or bubble, like that. So this is like we can use different methods and we can just try to get the building, decompose them in terms of this, and that information gives much better structure for the amplitude. So this is why next leading order now become the new standard, like it is the new LO corrections, we can say, completely automated. There are different public tools to compute this next leading order computations. But that is not really the case when you go beyond the next leading order at a higher loop. Such a kind of decomposition, a generalized decomposition, is not really very known. For example, for the Z gamma gamma protection, there are some kind of building blocks, but there could be something better form. We don't really know. Or if we consider some other process, the building blocks are different. So we don't have a general method to which building blocks it could be decomposed, and that makes the problem also, like this information is not there. But still we are in a better position because, let me explain that. What I meant is this Feynman diagram, for example, if we have 2 to n process, and depending on whatever is the external state, there are polarization vectors and spinors, and then we have, earlier I mentioned that there is loop corrections which basically give rise to a Feynman integral, and this integral is basically coming because of the reason that these quantum states, we have to take care of their, probably the momenta there, we have to take care of them from all the correction, like 0 to infinity, we have to take care of all those corrections, and that will give rise to the integral. So Feynman diagram computations will be having such kind of integrals, and that depends on the dimensions and external and loop kinematics. And when we look at, again I'm taking this Z gamma gamma as the example, when we look at this loop, number of loop integrals, at the next leading order, this become 1000, and when we go to the 2 loop corrections, it become really like this, like for this process it is 500,000, and it becomes like millions and billions of such kind of integrals. And when we have such large number of integrals, it is really difficult to handle them. But still we are in a better position. What I meant here is that by this time we already know that there are like all these integrals are not really independent. They have linear relations between them, and which can be found by using integration by parts identities. So we can systematically eliminate. There are algorithms to do that, such kind of elimination using integration by parts identities. There are other things as well. We can use symmetries as well, and then from there we can try to find out a system of linear equations that will try to reduce this whole set of integral to a minimal set of basis integral or master integrals. Then our computation of this whole set of integrals become reduced to compute the master integrals. Okay, so here I have given an example. It's just from the one loop again. For 2 to 3 process, this is like a pentagon diagram, but we can express them using IPPP identities. We can express them to a more simple structures, like compared to the pentagon function, we can express in terms of the box integral. This is a simple example at the one loop, but we can actually say in the 2 loop how it will be reduced. The complex integral we can reduce down to a simple integrals. Yeah, but here it is not really, here you can see as a P1 plus P2 is going as, it's a kind of topology given. So it is very powerful technique, and it's actually one of the bottleneck in the next leading order computation. So just to say, these integrals now, these 1000 integrals reduced down to 51 integrals, and this 4 lakh integrals now reduced down to few thousands of integrals. So our aim is now to compute these integrals instead of all those ones. But yeah. Yes, there are tools. Yes. There are tools for all these things, for generating the diagrams. Also, the algorithm to get this systematically, these IPP identities. Only problem is that how we use that and how we actually. So here it is this basis integral I told, which could be any arbitrary basis integral. Like the number could be same, like there is 51 integrals, but it could be anything. It depends on us which one we want to choose, and depending on that, our like the problem will be also different. Like the complexity of the problem will be also different. So there is an like experience there to come up with what could be the good set of basis integral. But there is algorithm in general to do such kind of things. Yes. Oh no. You have to feed everything at each step. So it's like, yeah, to gather many things you have to also feed the see, we can make it like the computer program itself choose some kind of basis, but that may be just, if you even choose the basis, it will take weeks to get the reduction. But if you don't give a thing, it will be just going on and it does not converge, because it is like, if you know final destination where it has to go, then it is easier to do that. But if you don't give that, probably it is difficult to get such kind of things. Yeah. If it is independent, yeah. There could be like, so when I say master integral, it may actually vary, yeah. But that is also coming from our limitations, right? Once we already know the minimal set that really give rise to all the integrals, then that number will be same. But probably we don't know that. So, okay. Like this. Yeah, that can be situation is there, and there are different tools, and probably different tools will give you different number of master integrals as well. Yeah. This is there. That is true. But I was understanding. Okay. Okay. Yeah, but what you told is correct. I mean, I have even experience on that. But I was thinking that is our limitation, that we are unable to really see what could be the minimum number of master integrals. For example, for the simpler process, it really number is the same. Whatever you choose, the integrals would be different, but the number is the same. And that is why we say it is the independent set of integrals, and from there you can produce all other integrals through linear relations. But there are these cases where, yeah, it is not really. To prove that, okay. Yes. Like, yes. You can say in this way. We know that it's asymptotic, but probably we can make naive arguments, like how we see that how Feynman diagrams, like it grows factorial. So these coefficients we can give rise to, like it goes like a n factorial power with coupling is alpha to the power n. So how much, at which range it will be going to this like breaking the series would be something like beyond 20 or something like that, just from the naive picture. It may not be correct, but we can only see what we really get from the experiments and theory, whether we are really going to such kind of divergences that we did not reach yet. Like people have calculated 5 loop for the coupling constant. We did not still touch any asymptotic kind of problems. It is, until now, everything is convergent. So, yeah, we don't know, at some point something will happen. We don't know. Yes. I mean, it is. Okay.
Okay. So I think all I'm saying is that quadratic properties also depend on the external momentum. Only for simple one-dimensional physics
really say about yeah, that's true. So I don't know whether there is really an explanation for where it will be breaking, whether we know about it.
It's more an art at the moment.
Yeah, and it seems like working when we compare with experiments as well.
And the second question
Yeah.
is that this minimum set is there some sense in
It is not really. It is a kind of like basis in a vector space. We can choose any of them. It's not really unique. But that's what I was mentioning, that probably the number is unique, but Anand was saying that probably that is also.
kind of problem comes up all the time when you look at modules in algebra. Where you have
Yes.
and there are general theorems which tell you that for modules of a polynomial, these are problems I don't know.
No, people actually use this as well in order to find out relations. Yeah, but I don't really work, but I have seen people have worked on that to find out more relations.
There is no, that example that I know, there is no canonical choice of minimum state.
Yes, that is also true here. And
So there is a maybe you know there is a well-developed technology called Grosvenor basis.
yes, yeah,
Polynomial identity
Yes.
for modules of polynomial rings.
yes,
Polynomial rings, and if there are CCGs,
yes,
then there are codes like that
yeah.
tell you the constituents.
Which-
Grosvenor basis help you to identify the
Which could be the better ones, right? Yes. Yeah. There has been studies over that as well. Just I am not very aware about how, but yeah, that is true, and I actually use those algorithms as well. But I don't know the details of such thing, how they actually come up with that thing. A bit about that I will talk in the later section, but not a lot of details here. Okay, so as I mentioned, this integration by parts identity is very powerful, but the price we have to pay with that is that what it comes with when it reduces these integrals to a master integral, the coefficient here become a huge linear system. It will be in the size of like gigabytes or terabytes, where we need computer. It's like a real like good computing system in order to handle such kind of big rational coefficients. And like when the number of integrals are much large, there are like large number of identities, and also the rational function become very complicated. So it is very computationally expensive. So once we start using IPPs, we have to also take care of such kind of system, how we can go ahead with this kind of linear system. So instead of solving the integrals, it turned into a linear algebra problem where we have to deal with how we can get a better things about this, how we can deal with it. Another thing is this master integral itself, we have to solve them in terms of some like non-special functions, which like what I meant by non here is that we know what is the properties of such kind of mathematical functions, we know the limits of them, branch cut of it, and then how we can series expansion to that. So this kind of thing. So there are like different level of problems that we have to deal with, even though we do IPP things. And when we go like with number of loops and physical scales in the problem increases, this become much more problematic. Now, but you have to know. So many times it has been seen that that is also one of the things, like if probably you have a better basis, you can solve them in a better way, but still it is not a generalized, it's also a well-known problem, like how you can actually express in terms of some mathematical functions, not really generalized thing. And yeah, it's right now it become like state of the art become like that. Probably you have to get some kind of numerical solutions to that. But of course there are efforts to understand what could be the structure of these master integrals, connecting with the geometrical properties and things like that. There are works along that directions as well. So let us briefly see how we actually deal with such kind of complexity. For example, first we take the computing complexity. So in the last few years has been seen numerous efforts and coming up with powerful algorithms to handle such kind of things. One thing is usage of finite field. Basically, when we have such kind of large system of equations, if we want to really do analytically, that become much complicated, probably we cannot handle them. Instead, what we can use is the finite field, which is basically do the sampling, numerical sampling. Instead of on the floating number, we take integers, like integers of the prime numbers, and apply this, like in our problem, basically the external kinematics is the variables. So for these variables, apply these computations with different such kind of integer samples to many large kind of evaluations, such that there is a way to reconstruct back what could be the analytic structure. So by doing this many numerical samples, we can reconstruct back whatever is the rational coefficients analytically. So there are algorithms to do that using finite field techniques. And now this technique has become standard for state-of-the-art techniques. We have to go through this numerical sampling. But by doing that, we can actually avoid this intermediate step when we do this IPP, because the whole system we can actually put in this, the IPP we can do in this using these numerical samples. So which actually allow us to avoid the rational functions well in the intermediate step, and we can only reconstruct the final step, and that give rise to a better looking solutions or more compact structure to the huge rational functions. Yeah.
Clarify.
Yeah.
When you say finite field,
Yes.
does it mean that you are just looking at a finite number of samples, or do you
Yes.
mean
Finite number of.
finite field as in ZP?
It is ZP. Yes. What I meant is ZP. So it is prime modular. Yeah.
So then I would like to understand why finite number of samples is
Because that.
working with ZP.
Probably to decrease the degree of such kind of large number, like we cannot go beyond some large number. So that is why probably it is better to use the prime number over modulo this p. That is why it can reduce the degree of such kind of large number. This is what I understand what could be the reason. But actually, the thing is that there are actually algorithm right now. There is something called finite field techniques. It is from the computer science things, and that has been taken here for the multi-loop computations, and people actually made methods and implemented them in different programs. So we can really use such kind of programs. We have to know what are the good way of using that, and then through that actually it gives rise to very large prime numbers, and it can really apply for many numerical samples. But the seed number of these samples we will be giving is too much. It could be millions or billions. So we need huge computing system to do that, and parallelization that is required in these cases in order to do this kind of state-of-the-art techniques. That become like a new standard to get into the things. IPP is the integration by parts. Sorry. Another thing that we can do is that there are like large number of identities. If that is one thing that you mentioned, the syzygies, we can try to identify some kind of algebraic methods where we can try to identify redundant identities. Like many of these identities will be the similar one. Then we need methods to identify what could be those redundant ones. Then we can remove such things. And also we could be having scaleless integrals, that integrals are zero. So if we, before doing the IPP, if we apply some kind of methods to understand this kind of redundant identities and zero integrals, that will slightly reduce the number of identities to be solved using IPP. And then we can also use the symmetry properties of the amplitude, or how understanding the singularity structure and handling the system in a better way, that also reduce by some factors the whole setup, the whole computational things. So there are different methods that we can try, and some of them we have been used in our one of the recent work, and that I will be talking in detail tomorrow. And what about the integral part? So I have already talked a little bit about how we can deal with the computational complexity. Now the integral part, again there are direct integration method using Feynman parameterization and so on. But when we go beyond some level, it becomes like probably that is not a better representation. But it has been found recently that there is this method of differential equations, which is basically consequence of IPP system. But what I meant by that is that if we try to take a derivative of this master integral with respect to our external kinematics, that momenta and external invariance, if we try to take that derivative, whatever the integral we get, when we again do the IBP to that, it will come down to the same master integral. So basically what it will be giving rise to is the first order coupled differential equations. So instead of solving integral, that will reduce down to solving first order differential equations method. And this, the M here will be kind of depending on how much master integral we have, that will be n by n matrix. So I am not saying that this become like now straightforward to do that. It has been realized that even though it is a differential, we have to solve the differential equation, it is not really straightforward. It is also very complicated to solve such kind of differential equations. But it has been found that if we can write in a peculiar form this differential equation, which is called a canonical form, where we can basically factorize that the complete dependence on the dimension of the problem. If that is the case, then it is a well-known problem. Those differential equation has a solution in terms of something called iterated integrals, or we can express them in terms of like generalized polylogarithms. So once we can, so that is what I meant by this basis integral. If we choose in a good set of basis integral, probably we can express them in terms of a canonical form in the differential equation. And once we have that, then the solutions are known in terms of generalized polylogarithms, and then there are libraries to solve them. So if we are in that state, then we can say that our problem of computing the integrals has been solved. But many times we can also see that it is not always the case that we can actually get the canonical form to the differential equations. At that time, we have to think how we can actually solve the differential equations. And people are in you need the boundary conditions as well. But right now we have tools actually at least to check. If you know at least some good boundary conditions, like some phase space where we can actually have a better, we know actually what is the integral, then it is okay. But now there are tools that we can actually make use of this. We can understand what could be the boundary conditions. Yeah, but yeah, that is also good information that we have. We need the boundary conditions. And now we are in a now we are in a state that where we have more, like for example, if we take the electroweak correction, there are more mass scales coming to the picture, and it's not really, we cannot really use other methods. So what we can use is a semi-analytic method, which basically these differential equations we can solve numerically by getting some kind of generalized power series, and that is also now another direction that people are now working and to make an algorithm through that. Okay. So D is the dimension, okay, and X is the extent. Yeah. So X is the kinematics, like it could be S, T, you can, exactly. Yeah. Because in the 4 dimension it is, we have this dimension parameter epsilon, so basically it is D minus 4. So when I meant by canonical form, which is basically means that this D minus 4 you can actually explicitly factorize from the matrix. If that is the form, then you can expand the whole differential equations and then solve order by order in the epsilon. That is why it become, canonical equations become like we can solve this differential equation if it is in a canonical form.
And I understand this is a popular loss, but is this a first order equation you have in mind, or
yes,
it's always the
first order differential equation? Okay. So I think I have given a bit overview on how we can deal with the computation complexity and how we can solve the master integral. What are the methods, at least, to solve these kind of integrals? Now, another problem that we have in the perturbative series is that, actually, how much time I have left? 2 minutes, okay. Okay. So another problem that we have is the divergences. So we can get divergences coming from the ultraviolet and the infrared region. For example, for the ultraviolet, it is when the loop momentum is much larger, and then we can use renormalization in order to deal with that. Now, another kind of divergences can come up that is coming from the infrared. Basically, for example, if we take like an emission from a quark line, the propagator here, from here we can see the structure will be looking like this. So what could be the source of this divergence is when the emission, this this emission is soft, like the energy of such emissions are much, much smaller. If that is the case, there will be a singularity. Or if this emission is collinear to whatever is the external state, in that case also there will be a singularity. So specifically infrared divergence comes from these soft singularities or collinear singularity. But it is a general idea that we have that if we take all the contribution from the virtual corrections and the real emission, we can see that these divergences cancel when we add them together. Only thing we have to notice that in the real emission, there is the phase space is different, like there is an additional phase space because of the real emission. So we have to actually, to get it to this picture, we have to actually get the first integration to get to this singularity structure. But once we have that, it is infrared safe. So for simple process, these kind of things are very manifested, like we can really compute both the virtual corrections and the real corrections and then cancel these divergences. That is straightforward. But that is not really the case when we go beyond simple process. Where we can see is that doing such kind of real corrections in like this phase space integration, that is usually done using numerical methods because it is much complicated to do such kind of phase space integration. So usually it has been done using numerical methods. But before doing such kind of numerical evaluation to this phase space integral, we have to first take care of these singularities. So we have to remove the singularity from the real emissions before doing that. And the general methods to do that is known as the subtraction method, which basically has taken care of these infrared divergences from the real emission such that it will be giving rise to a finite integrand we can give rise to, we can actually do the numerical evaluation. So I just want to mention that there are ongoing efforts to get a generalized structure for this subtraction. A little bit about that I will be talking tomorrow. Another things that comes is the what I mentioned as the resummation earlier. What I meant is that even though this kind of things, the singularity cancels, but there could be large corrections coming from the logarithmic term in the sum of the phase space region. And in such cases, we have to somehow deal with these logarithms to the all order in the perturbative series. And that kind of method is known as the resummation. Again, details of this I will be talking tomorrow. So these kind of things we have to also handle in the perturbative calculations. Sorry. I will be telling briefly about all these methods. So this is the summary of whatever I was mentioning in the perturbative calculation. What we are dealing with is the scattering amplitude, where loop corrections and real emissions are there, and what are the things we have to handle in both of them. We have the large setup of this IPP that we have to handle, complicated rational functions, and then we have to also express these integrals in terms of special functions, and we have to also deal with the divergences. And then real emission as well, there are subtractions and resummation we have to take care in the real emission. Once we have all these things, we get the scattering amplitude, and from there, by integrating them, we get the partonic cross section. And once we deal with the non-perturbative PDF, we get the hadronic cross section, which we can really compare with whatever is the experiment. Okay. So I just want to mention where I will be finishing in 2 minutes. So I just want to mention where exactly in some of my process that has been that actually given the relevance at the collider phenomenology. So one of such calculation, the light by light scattering, my recent work, which I will be talking more in the tomorrow's talk mainly. It will be completely light by light scattering, where I will mention everything whatever I was telling today. But just I wanted to mention that this computation, where we have used some of the method that I already mentioned, but the phenomenological relevance comes when, for the new physics kind of thing, where axion or graviton-like particles, for such kind of things, this process from the standard model corrections become the background for such kind of new physics. And we have computed the precise computations. Whatever was the earlier one was the one loop computation, so we have added the next leading order correction, next corrections to that. And that basically helped to give more stringent constraint to the coupling to the axion, to the photon coupling. So CMS has taken our result in order to get the most stringent constraint to the axion-like particles coupling, as well as graviton-like coupling as well. I also just want to mention in a few words about the Higgs pair production. My prediction means they have taken our results as the standard model background in order to get that. CMS is the red part is the CMS, the newest constraint. Again, for the Higgs pair production, which is one of the important channel in the LHC to get to the Higgs self interactions. And there are, as I mentioned earlier, there are many sources of theoretical uncertainty, and one source of theoretical uncertainty is the scale, unphysical scale in the problem. using resummation corrections to this Higgs pair protection, we could actually go to less than 1% uncertainty from the theory. So this has been also, like from the theory side, this is the most precise theory predictions. For the case of this, one of the corrections that we could take care of. But of course, there are other uncertainty, for example, missing mass uncertainty and coupling uncertainty that we have to still deal with. But one of the uncertainty we could deal with using our computations. And that has come to the conclusion. So basically what I wanted to try was to convince that collider physics remain some of the most accessible experiment till now. From from the last century, we have collider physics experiments that actually help us to go forward and find out better, deeper structure of scattering amplitude and the whole deeper structure of nature, I could say. And then still we are getting fundamental discoveries, the last of which we can say that the Higgs coupling to the fermions is something that we have recently discovered, even though that has been predicted by the standard model. So there are, from the experimental side, there are well-defined plans for the next 20 years. So it is very crucial that to fully explore this physics potential of these colliders, it is very crucial that we get precise and accurate understanding of the standard model itself. So along with other searches like dark matter and neutrinos, other observations, it's also very important that we pursue the collider physics as well, along with the support from the theoretical support in order to understand what could be something beyond the standard model. And beside all these things, such kind of computations also give us motivation to solve these such kind of challenging questions and also advance our techniques and also come up with public tools and framework which could be useful for other areas of physics as well. So yeah, thanks very much for that. Yeah. Yes. 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 For example, this light by light scattering. What? No. Yeah. I don't know whether, because there the non-perturbative effects also come up, right? So yeah. I'm not very aware about how actually people study this nuclear structure and things, but it's not really. If there are non-perturbative techniques to do that, I am not really aware about a lot about it. Yeah. So, yeah. For example, you have a master integral. You take derivative with respect to some kinematics, okay? Like for example, S, Tu, this kind of external kinematics. You get some other integrals. It could be any integrals. But then you can again do the IPP to that. That will give rise to the master integral, right? And from there you get to this first order differential equation.